Hello everyone, Dr. Ziad Tahir here. This video tutorial is about transient heat transfer through double pane glass window. And that is a problem description. A double pane glass window shown in the figure consists of two 4 millimeter thick layers of glass. And these are the thermal properties of glass like thermal conductivity 0.8, density 2500, spec specific heat capacity 800, and that is separated by 10 millimeter thick stagnant air space. And these are the properties of air. The inside room temperature is 20 degrees Celsius with HI, that is convective heat transfer coefficient 10, and outside temperature -10 with convective heat transfer coefficient as 30. So that is all description. And then to model that in Abaqus, so assume height of the window as 30 millimeter. Although 30 millimeter is not a realistic one, but because the formula for both conduction and convection that uses cross-sectional area, so then uh, I am using that unrealistic one. So plot temperature variation at both surfaces of inside glass layer and outside glass layer. So temperature variation of both surfaces of inside glass and both surfaces of outside glass. So to solve that problem, I have designated inside glass as 1, air as 2, and outside glass as 3. So this problem is actually a modified version of the problem 13.9, that is 13.9, but I have modified it because this is for the steady state. I'm using it for transient. It is from chapter 13, heat transfer and mass transport of this book, a first course in finite element method. So here are three steps in Abaqus. The first one is model, to create model or modeling, then analysis, and then visualization of results. These are the three main. So before modeling, it is important to set units. So either meter, degree Celsius, and rest of all like as thermal conductivity and heat transfer coefficient in watt per meter per Kelvin or watt per meter square per Kelvin, or the other set is meter Kelvin, watt per meter per Kelvin, watt per meter square per Kelvin. So these are the set of units which are necessary. So for conduction and convection, if thermal conductivity is watt per meter Kelvin and the temperature is in degree Celsius, so it doesn't make any difference because the equations uses delta T and delta T remains same in both. So for this problem, like K, that is watt per meter per Kelvin, is C is joule per kg per Kelvin, but because it's only conduction and convection, so it doesn't make much difference about that. So before start, work directory need to set, so all that data is going to save in a specified folder. So for this one, I have that chapter 13 folder. I want to save everything in that one. So for that, I have here Abaqus. So in Abaqus, here file, set work directory, and that is work directory is being set. So I am using Abaqus 2020 version. Now the first step in modeling is to create part, and part is 2D planar deformable shell. So in Abaqus, here you can use that module and then model tree for part. So I have designated like parts as 1, 2, and 3. In inner glass or inside glass as designated as 1, air as 2, and outside glass as 3. So I am taking it as part 1, part 2, and part 3. So that is part 1, 2D deformable shell and approximate size. that is actually double of that maximum dimension. So, so the maximum dimension is assumed height of the window as 30 millimeter. So here I am taking it as, let's say, 60. So continue, and then I'm going to draw part 1. Part 1 is a rectangle and with width as 4 millimeter and height as 30 millimeter. So there are different options here. Connected lines can be used, and then connected line as rectangle can be used. So starting, let's say, from origin. So, and then other dimension along x-axis is 4 millimeter, and along y-axis it is 30 millimeter. Okay, so long x-axis is 4 millimeter, and then 30 into 10 to the raised power minus 3. Enter, so that is cancel procedure. That first part has been now created. So here I can add auto dimension to check if everything is okay. So done. So that is 0.03 and that is 0.004. So that is first part done. And now the second part, 2D deformable wire and 60 millimeter. Now for the second part, it is 10 millimeter and 30 millimeter. So I can use that now another way of it. So just a random rectangle, and that dimension is 10 e raised power minus 3, and then this dimension is 30 e raised power minus 3. So then this one, oh, oops, there is, I think, something wrong. Let me correct it. Once again, that random triangle, and that is 10 e raised power minus 3, and that is 30 e raised power minus 3. 3, and then you have that rectangle. So, like, these are the heights. I just want to drag that somewhere there. Okay, so that is the part, and cancel procedure done. And now the third part, click on that part 3, 2D deformable shell, and then approximate sizes, that is 60 centimeter, and it is again the replica of that what we have drawn already. So I'm using that random triangle, and for that one, this dimension is 0 point, like it is 4 e raised power minus 3. Okay, and this dimension is 30 e raised power minus 3. Okay, so that part has been created. That's the third part is being created. So let me drag it somewhere there. Okay, now these three parts are created. Done. So that is a part 1, then part 2, then part 3. Part 1 and part 3 are identical. Okay, next step, need to create surfaces on each part, and that is surface geometry type, and these are required to apply temperature, coefficient of heat transfer coefficient, and contact between the points. So surfaces are required because on the at inside surface and outside surface temperature and T and H are required, and then on those inner surfaces, so for that inner surfaces contact is required. So for each part need to create surfaces. So that's a part 1, and then you can see surfaces, double click on that. So I am going to use right and left, continue. So that is the right edge, that right edge, and then then is left edge, and that is left edge. So surfaces for all parts has been created. That is for part 2, left, right, part 3, left and right. So these surfaces are created so that to apply temperature and coefficient of heat transfer and contact. So that is done. Now this part is not necessary, the next one. So in create Datum plane. So Datum plane is usually created, or sometimes the partition is being created so that you will get your required specific points on that part. So I'm just creating that Datum plane for each model. So that is part 1. Here is part 1. So tools, Datum, Datum plane, midway between 2 points, and these are the 2 points in between them. I want that is your Datum has been created. And similarly part 2. So that is created. Similarly part 3, and then Datum is being created. Okay. Next step is to create material, and there are two material. One is glass and the other one is, so these are thermal conductivity, density, specific heat capacity of glass, and then for air. So for that purpose, property, or here are the material, double click on that. So material is glass, thermal conductivity. So thermal conductivity of glass is 0.025. That is the thermal conductivity of glass, and then specific heat capacity of glass, that is 800, and then density in, that is general density, and then the density is 2500. Okay, so here thermal conductivity 0.05, specific heat as 800, and that is the density. So that in material, that glass has been created. Similarly, glass has been created. Material is conductivity for glass 0.8, then density, specific heat capacity, and similarly I have created here conductivity, then density, and then specific heat capacity. Next step is in the property module, create section and then assign section. So because there are there are three parts, so I'm going to here section 1, solid homogeneous, and then the first one is the material is glass, so that first section is being created. Then section 2 is air, that, and then the third one is section 3, solid homogeneous, and then it is again glass. So here you can see that, so section 1, that is the section 1 glass, section 2 air, and then section 3 again glass. So once that is then assign sections. So here assign section, and no need of creating any set. Part 1 assign section. So select that one, done, and for that one is a section 1. Then is part 2 assign section, select it, done, that is section 2, and then part 3 assign section, and then that is section 3. So here you can see that 3 sections have been created. Then here 2 materials, they are being created, and then section assigned, and then next step is mesh. So it is seed part, assign mesh control, mesh part, and assign element type. And this is required for all these three. For all these three. So part one, here is the mesh for part one, seed, and I am going to use here as global size as point. It can be used as 1 millimeter or it can be used as 0.5 millimeter. So let's say I am going to use it as zero point 0.5 millimeter. So zero point 0.5 into 10 to the raised power minus 3. Okay. Then here assign mesh. Here assign mesh control is a quadratic, free, and medial axis. Then mesh and then element type. In the family, it is heat transfer, standard linear. Then part 2, seed part, the same size. Apply. Okay. Then mesh control, quadratic, free, medial axis. Then that is, and then here you have again heat transfer from here. And then the part 3, again the same one, zero point 0.5 millimeter or zero point 0.5 into 10 to the raised power minus 3. Assign mesh control, quadratic, free, medial axis. Then mesh part, yes. And then assign mesh control, heat transfer. Okay. 3 parts. You can see part 1, part 2, and part 3. They are meshed. Next step is to create set. So because we are looking for some specific points, so node type, and that is required to plot temperature at specific points. So I need to plot temperature at inner and outer side of the part 1 and part 2. So that is a part 1. So in these 3 parts, so for part 1, uh, then here double click on set. So that is, let's say, left node on that part. So that is the left node. You can see in the set, and then right node. Okay, that done. So that is part 1, and similarly I need to do create set for part 3. So that is left node, and then right node. That is done. So now you can see that is the right left node, that is the right node for part 3, and for part 1 that is the left node and that is the right node. So these 4 set has been created. Next step is assembly, and then to first to create an instance and then to translate instance. So that is a part 1 followed by part 2 and part 3. So I need to arrange those parts in assembly. So for that one, in the module assembly, and then here create instance, part 1, part 2, and part 3. So these are the 3 parts. In assembly default, I'll go to the parts and to check that where are these parts. So in the assembly, that is a part 1, that is a part 2, that is part 3. So I need to keep that because it is here. So I need to keep that part 2 towards part 1. So for that purpose, translate instance. So that is selected. Select the instance, and then that is the point I want to translate that here. So you can see that, so that air part is being translated. Okay, so it's a now I want to translate that part 3. part 3 next to part 2, and for that one, translate instance, select the instance to translate, and then I want to translate that point to there, and now you have seen that. So that is part, all those three parts. So that is part 1, that is part 2, part 3. So now they are being assembled and translated and assembled. Next step is to create step, and that is a heat transfer. Although it is a transient state, a transient problem, transient heat transfer, but initially I'll solve it using steady state and temperature is 1 second. So here steps, step, and then create step, and it is heat transfer, and that is heat transfer selected, continue. I'm going for transient with time period of 1. So that's done. So you can see here the heat transfer step is created. If I double click on that, so it is type is heat transfer and steady state. The next step is to define mechanical contact between the two edges, and that will go in the interaction module and create instance constraints. So you can see here, so the constraints are directly there. So you can click on that, and it's a constraint 1 and type is die, continue. Then it's a choose a master surface. So usually master surface is from where the heat is flowing. So that one surface, I have already created that. So I'll go to the surfaces, and that is part 1 and that right surface. And then again surface, and that is part 2 left surface. Okay, so you can see that these are being highlighted. So okay, and that constraint 1 is being developed. Otherwise, you can go into interaction, and that's the constraint 2 type tie. Continue. I want to develop that here. So surface, and that is part 2 right is the master, and then part 3 left is the slave surface. So you can see that now constraints 2 constraint, that is a constraint 1, and by double clicking that constraint 2, that is being now mechanical contact between the edges is developed. So next step is create interaction, and they are to apply temperature and edge. So that is surface film condition. So for that one, here you have interactions. Double click on that interaction. So that I am going to say it as inside, and step is heat transfer, surface film condition, continue, and it says that which, so part 1 left surface I am going to select, and then you will have that. So film coefficient at inside it is 10, and the temperature at inside is 20. Okay, and you can see that an interaction is being developed. Otherwise, you can go to interaction module and create another in, and that is for outside. Surface film condition, continue, and for outside that you can select in the viewport, and that is the surface. Otherwise, you can select from the surfaces. Okay, for outside, uh, film coefficient, like the coefficient of convective heat transfer coefficient is 30, and then it is minus 10. Okay, so that is now interaction is being developed. So now all modeling part is done. So once all that modeling part is done, so then I can go to analysis. So job, create job, data check and submit. And remember that it is still steady state for time equal to 1. So I'm going to rename that model as double pane window. Double pane window. Okay. And then in the job, is double frame window, continue, okay, and then you'll have here submit. First, you can apply data check on that, data check. So data check submitted. It will take some time to run, and then check running completed. Okay, so then I can submit it. Okay, so the purpose of this with the steady state, first, because steady state uh, analysis is a quick one, and with the steady state, either you will see that how much time, like time step you need to give to get your results, and that are the here is completed. So now that analysis is completed. So now once analysis is completed, then I can go to result and then visualize those. So for results, just click on that and then you'll see those results, and that is a deformed shape, like that is a heat flux, it is constant, and that is temperature. So that is the temperature, and using steady state, I can see that on inside it is 14.47 temperature and outside is -8. So let's say I am going to snip this one, okay, and I'll say keep it somewhere. Now with steady state, it is now clear that everything is okay, model is fine, and it is working. So now once it is done, so then I can run it for transient. Okay, so I need to go back again to the model, and then that is a step. Create step, heat transfer, and then time is not sure. Okay, so we can start with, let's say, with 10, 10 minutes. So steady state is 1 second. So let's say for 10 minutes. So here I'll go back to step, right click on that. So previously steady state, now transient. And for 10 minutes, let's say 600. Okay, and in the incrementation, that is 600. Initial is usually zero point 0.1, and the minimum keep it as 1 into 10 to the raise power -5. So initial zero point 0.1, minimum 1 into 10 to the raise power -5, and the maximum number of increment, let's say 100, and then maximum allowable temperature as 1. So initially, I am going to check when whether it converts it like for 10 uh, minutes or not. Okay. Then again submit it. So it will take some time to complete. So it is being submitted, it will run, and then it will complete it in some time. Now that is completed. So then you can go to the results and then to check that if it achieves steady state or not, NT11, and that is NT11. So you can see for steady state it is 14, and inside is at 8 and the outside is at -7, 8. So it means that after that 10 minutes it will is not going to achieve that steady state. So then you need to increase time. Okay, so you can increase that time. So let's say I'm from 10 minutes, I'm going to increase into 2 hours. So 7200 seconds. Okay, and I'm going to submit and run it, and then so it is completed for 2 hours. In the results, okay, so you can see that it's almost the results are almost achieved for when time step is 2 hours. So 14.47 and the minimum is 8.16, and here is 8.16. So maximum and minimum temperature. So like here, the temp time for this particular problem is 2 hour or 7200 seconds. So for that one, it achieved steady transient state. So when it's done, I can go back to visualization, create XY data, and ODB field output. Temperature variation at both surfaces of inside glass layer and outside glass layer are required. So for that one, now that I can go here, create XY data, ODB file output, continue, here unique node, NT1, and then node set. So I have that part 1 left node. So that is on the glass plate inside. I'm going to plot it and just change it no fill. So now you can see that the temperature changes with time, and that is for 7200, and it is almost asymptote of that one. So that plot can be saved as, so that can be saved in, so it is being saved. Okay, so X data extracted using default name. So XY data are saved only for the current Abaqus section. So then here, this is, let's say, I'm going to rename it. So that is uh, inside. Okay, that is for inside glass, and that is left of that. So inner glass, left of that. Okay, then that's the right node for that. That is being saved. Okay, so it is being saved here. I am going to rename that as, so that is right. Okay, and similarly I can plot all other. So now these four are being plotted: inside glass left, inside glass right, outside left and right. So I can plot them simultaneously, both of those, that is inside glass left. So you can see that they are going to achieve same temperature, uh, like their distribution. And then here you can see that inside and outside of the glass. So that is the temperature variation at both surfaces of inside glass and outside. And similarly, if you want to plot, continue, and then heat flux magnitude, not the all of it, and then node. So that is heat flux magnitude over time. So like the maximum is 179 for that one. So this is all done of this problem. So just a quick recap of it. So in Abaqus, there are three main steps of modeling, analysis, and results. So you need to check unit first, set work directory, part. You need to create part, 2D planar deformable shell. Then create surfaces. Surfaces are required to apply temperature, edge, and contact between the surfaces. Then create a datum plane. The purpose of that datum plane is to easily identify that point where you want to plot something. Then you need to create material, and for this one you need to put thermal conductivity, specific heat capacity, and density. Then you need to create section and assign section. Then mesh, seed part, assign mesh control, mesh part, and assign element type. Then create set of node type to plot temperature at specific point. Then the assembly, create instance, and then translate instance to, so that they will be aligned as it's required. Then create step, and then create constraints, so they are to join the surfaces. Then create interaction to apply temperature and edge. And for transient state, now for transient state, it is easy that you first check everything using steady state condition. And for that steady state condition, whatever you will get, take as a reference. And then once it is running for the steady state, then uh, change the step to transient, and then time t, you need to check that so that you will get results very similar to, not similar, but closely similar to transient, a steady state. I hope you like this video, and thank you very much for watching. If you can leave your feedback in comment section, and if you want me to record any other video like that, or your specific problem in heat transfer, so then you can leave a comment and then I'll try. Thank you very much for watching.